Welcome to Rambus Design Summit 2020. Morning, everyone. Over the next 30 minutes, we'll talk about securing the semiconductors. And during the presentation, if you have any questions, please press the Q&A button at the bottom of the console. Now, let's talk about securing semiconductors with security by design approach. You'll hear two terms quite often during this session. One, security by design, and the second, zero trust environment. What do they mean? Well, zero trust, current geopolitical situation and increasing adversarial posture from hackers is leading to zero trust environment. Here it's hard to trust anyone and even harder to build fully vertically integrated supply chains. So we are effectively operating in an environment where we can't trust anyone, and that's why it's called zero trust environment. And semiconductors, especially security around semiconductors, need to be re-architected to be able to make effective security in this zero trust environment. So we'll touch upon this. Second, security by design. It means that we start with security by design mindset when we are starting chip at the architecture stage. And that's the only way to truly secure semiconductor devices, their supply chains, and their life cycles. Let's start the presentation. So this slide provides a high-level overview into three categories that make up the end-to-end security for semiconductor infrastructure. The first of these categories is chip design, securing the device by itself. Second is securing the supply chain in the manufacturing part of it. And the last part is device life cycle, which is securing the device once it is out of the manufacturing and out in the field. So let's start with the chip architecture first, the chip design part. Here, the security must be a primary design goal. Protecting a semiconductor cannot be an afterthought, and it must exceed realistic adversarial capabilities that we define, zero trust environment being one of them. And this means security has to be thought of at hardware level by implementing a true hardware root of trust that is anchoring all security functions across the chip. This security subsystem needs to be implementing the cryptographic algorithms along with attack resistance like DPA and FIA. In addition, implementing defense in depth, because nothing is foolproof even if you design it in hardware, and renewable security in case something gets broken or hacked or we find new zero-day vulnerabilities, so that the device continues to operate securely by renewing that security. Second box here, pertaining to manufacturing, whether we're dealing with global captive or third-party supply chains, they both provide significant risk to security on a device. And we must authenticate our chips in the manufacturing flow, regardless of where these chips are being produced. And this means provisioning chips with unique and immutable identity as they are manufactured. Now, the last part, once you have secured the chip with a hardware root of trust as you're anchoring all the security functions, and you have authenticated your chips during the manufacturing flow, now they go out in the field. And here, building on these two, we deploy cloud-based methods for field authentication, upgrades, feature management, and decommissioning RMA of the device so we can securely have this device operate in its in-field life. During the rest of these slides, we'll dive into each one of these three categories, especially about how they are implemented at an architectural level by security by design method. Let's start with chip design. When we are looking to securing a device, in order to protect anything, a device needs certain properties that it can trust. Now you could see from the chart on the right there is a trade-off between security and the complexity. The highest security device may also have, as you go in, it will lead to higher complexity on the chip. So to protect anything, this device needs certain properties, and those properties must be trusted to be unsubvertible beyond the capabilities of any reasonable attack scenario. What I mean by this attack scenario is, it's very easy to say my data is encrypted, but even encrypted data can be hacked with advanced attack scenarios. And that's what I mean by trusted to be unsubvertible beyond the capabilities of these attack scenarios. So we implement this by building multiple root of trust for securing each one of these properties. And we put that in an architectural thinking way, right when you are designing either the data flow or how you are storing secrets inside the chip. And you will see in the next slide how many applications actually can be secured by taking this approach. And in many cases, this given root of trust may be trustworthy only under one attack scenario, and it may lose that property in another advanced attack scenarios, whether you're looking at fault injection attacks or you are looking at side channel attacks. So sensitive security functions should not be run in your main CPU, so they can be protected in the right way with a given root of trust scenario that you are operating under. And that's the segue to the next slide, where we talk about how do we build this separate co-processing unit called a hardware root of trust to secure the device. So as you see the picture on the left, a true hardware root of trust can implement a host of secure functionalities. You can start with more on the basic side, where secure boot, secure data storage, key storage, and secure debug. It can provide various cryptographic accelerations, whether it's geographically related like SMX crypto, or some of more industry standard like AES and PKE. It can also provide attack resistance against DPA, the side channel attacks, as well as FIA, the fault injection attacks. So in conclusion, this root of trust is the trusted foundation that your SoC and applications use to build their own protection. This is a method, a co-processing engine that can actually vary its functionality depending on whether it's a small IoT device or a very high-end training AI data acceleration device. As you move towards the second box in that second slide earlier we talked about, where we talk about manufacturing in zero trust environment, let's first look at some of the threats that are out there in the marketplace. Inauthentic chips are on the rise. Every production environment is a zero trust environment, whether it's captive or third party, as we earlier talked about. And we see that counterfeit parts are putting military supplies at risk, because there is a difference between the military supply chain compared to the commercial supply chain. A typical military device has larger number of parts, and their life cycle is spread about 3 to 4x compared to a typical mobile device, where you see end of life is somewhere in the range of 2 to 3 years. While a device that's going out there in a weapon system can actually require the supply chain to be functioning for replacing RMA and the devices like that over a decade. So that really puts the military supply chain at a much higher vulnerability risk compared to a tighter run mobile phone supply chain that is usually spread a few years. And as we move over, continuing this, how does this demand from military and commercial supply chain get into an actual supply chain? Now, you see the attack scenario that we see on the supply chain continue to increase, and we see the part of the mistrust that's right now showing up because of the geopolitical situation. It's further complicating it. So it becomes super important that during the manufacturing, we can securely authenticate each chip. And that's what we are going to talk about in the next couple of slides. How do we do that? It's one thing to talk about that supply chains are insecure, but how do you fix it? We'll look at it very similar way how we looked at securing the device by going into a hardware root of trust with a variety of secure applications that can be completed with it, from secure debug, secure boot, all the way up to attack resistance to some high-end DPA, side channel attack, and FIA. So let's go to the next one. On the left-hand side here, on the picture, on the diagram, what you see is a typical crypto manager infrastructure product that consists of three functions or three components: crypto manager root server, the control center, and then the provisioning HSM appliances that securely authenticate semiconductors during manufacturing. So you see, once you have anchored these chips with root of trust, the next step is device provisioning. So we can securely authenticate and insert a unique immutable identity to these chips during manufacturing. One thing to note here is why this is so important. If you can't trust the device you are manufacturing, then you can't trust the data coming from that device. And if you can't establish authenticity of a semiconductor device in manufacturing, then that trust is broken at that part of the time, no matter how well we provision that device on the cloud for in-life life cycle management. That trust chain was broken during the manufacturing. So that's why authenticity can only be guaranteed during manufacturing by using what we believe is an automated injection of keys ID data into secure area of chips during manufacturing process. Now, this one line is probably the most important line to emphasize what we mean by security by design. You can implement many different variants of the provisioning, but you have to guarantee authenticity of that provisioning by following an automated injection or provisioning of keys, ID, and data into a secure area of the chip. It can be done. Once we do that, it can be done in trusted or untrusted facilities. So no human intervention is required or desired. And that makes it by design, secure by design, to operate in zero trust environment for manufacturing, because you are creating that authenticity with an automated injection. As you can see by now that you follow secure by design approach during the chip design, and then automated injection during manufacturing, and this creates a very strong foundation for managing chip life cycle in zero trust environment. Now let's look at the third and the last step of securing semiconductor infrastructure. Let's look at the life cycle. Once you have done the first two parts, how do we guarantee security once the device is in field? Well, we do that by having a secure implementation of key management service that will allow secure authentication of these chips on connected devices anywhere in the world. And it needs to work with major cloud providers like Azure, AWS, and Google Cloud. So this will allow high value in field transactions once the chip is in service, in field. Examples like chip and device attestation, key provisioning to support various applications and services, your software and firmware over the air updates, your feature enablement, so you can have the same SKU and monetize your device differently depending on who the customer is and who's using which features on that chip. You could perform high value in field transactions like deactivation of a chip when it's in wrong hands, or you could do RMA and many other functionalities like this. So by combining these three, it becomes an end-to-end semiconductor infrastructure enabling for security. And just to recap on the last two parts, why it is super important to go beyond root of trust to actually do the device provisioning and key management service is primarily supply chain security and integrity is increasingly important to semiconductor and device OEMs. And establishing a semiconductor provenance will soon be a requirement of most as you are looking through whether it's geopolitical situation or its regulations. On the identity assurance side, if you want to trust the chip data, you must be able to trust the chip. And that's why a unique ID must be established in an automated injection way during the manufacturing cycle, and then assured throughout the life cycle of a device with an end-to-end key management service that ties and takes advantage of the first two steps of chip design security and manufacturing security. So with this, as you move forward, let's just now look at one example of everything we have talked about so far. We talked about three categories. Now let's see in a typical superset of AI data flow and chip example. I'm combining here both the training accelerators as well as the inference kind of functionality, just to provide an end-to-end how AI workloads look like. So if you read from left to right, you've got some hardware accelerators that are loaded with training models. Then you have some training data coming over. In cases, you might have inference hardware and their models with the input data. And there might be endpoint hardware or edge devices that might be also interacting in this AI application use case. If we look at these 5 components that are the superset of AI workflows or components, you could see the top 3 small red boxes that are securing by implementing hardware root of trust in those places, whether it's AI accelerator for training, or AI accelerator for inference, or it's an edge device that is just processing some data or collecting some data. Having that root of trust will truly create security by design at the chip level. If you look at the bottom 3 red boxes, that's where the second and third part come in play. Once you have that root of trust inserted in an AI accelerator that is doing training or inference, you could actually provision it by doing automated injection of the keys or ID during the manufacturing, and then manage it through the life cycle. It could be an automotive ADAS kind of device doing that kind of AI or computer vision processing, or it could be a camera, or it could be some other sensor in the industrial automotive domain. But through this life cycle of 3 end-to-end security by design components at chip level, manufacturing level, and in life, we can actually have this end-to-end security implemented in an AI workload. So let's, in conclusion, let's look at everything. We looked at these 3, and these 3 can be secured, security by design with a hardware root of trust implementation, device provisioning in an automated injection way, and then tightly implemented key management service that takes advantage of the first 2. With that, concludes the security by design semiconductor infrastructure presentation.